Okay, so today for my project, I'm going to be doing problem 2.96 from the book. So what 2.96 has 3 parts to it, but the first thing we need to know about 2.96 is that it involves the ring, the map F from the ring of polynomials in X with real rational coefficients to the ring of polynomials of rings of polynomials of square root of 2 with real rational coefficients as well. Now what this map does is it takes X and changes every X to square root of 2. And what it does for polynomials in particular is it will take P of X to P of square root of 2. That's what that one will do. So our first part will be to prove that F is a ring homomorphism. And this will come in 3 parts for us to do. There are 3 things we'll need to prove. The first thing we'll need to prove is that for any arbitrary x and y, that f plus xy equals f of x plus f of y, and f of x times y equals f of x times f of y, and that f of 1 equals 1. So those are the 3 things that we're going to have to prove to show that this map here is a ring homomorphism. Okay, so after figuring out what we need to prove, the first thing I'm going to do is I'm going to define a few things for us. So we're going to let P1 of x and P2 of x, these are going to be polynomials for us that are involved in the ring, they are elements of the ring Q of x. Now, as P1 of x and P2 of x, as they're elements of Q of x, if we are to apply this map to them, that would mean, this would imply that fP1 of x is equal to P1 square root 2, and f of P2 of x is equal to P2 square root of 2. Now this will help us when we're going to star that, because that'll help us when we are trying to prove these facts up here. So the first thing we're going to do is we're going to come over here, and so for this, since we're defining P1 of x and P2 of x as elements, we're going to let P1, essentially P1 is going to be our x and P2 will be our y. So we need to show that f of P1 of x plus P2 of x is equal to f of P1 of x plus f of P2 of x. So we know, so we can do the left-hand side first, and we have f of P1 of x plus P2 of x is equal to what? But we can see from over here, we have f of P1 of x is equal to P1 square root 2, and f of P2 of x is equal to P2 square root of 2. So if we apply the map to both of them at the same time, we have that this is going to be equal to P1 square root of 2 plus P2 square root of 2. So now we have what the left-hand side is equal to, and then there are a couple ways we can show that it's equal to the right-hand side. I'll go with probably a more straightforward way. So for the right-hand side, we have f of P1 of x plus f of P2 of x. And again, from right here, from star, we have what those are equal to. So we know we can go straight away that this is going to be equal to P1 square root of 2 plus P2 square root of 2. And as we can see that the left-hand side is equal to the right-hand side, and that it is closed under addition. So we've proved the first part about it being a ring homomorphism. And then there is another way to do this where you could do like the pre-images of this and show that the preimage of that is equal to that, and the preimage of that is equal to that. That's another way you can do it, but this is a more straightforward way just to do the right-hand side as well as the left-hand side and show they're equal. Okay, so after showing that it is closed under addition, our next step would be to do this part right here, which shows that it is closed under multiplication. So for that, we're gonna, let me separate out a bit. So now we need to show that f of p1 of x times p2 of x is gonna be equal to, f of p1 of x times f of p2 of x. So this is what we want to show now. So our first step will be, again, go straight to the left-hand side. And when we apply the map of, and when we apply the map to this equation right here, we will again get similar to the additional one, where we'll have p1 square root of 2 times p2 square root of 2. And that's what the left-hand side is equal to. Now, I briefly mentioned how you can use like preimages to do this, to find out how that's equal to that. So we can do a similar thing here to prove that this on the left-hand side is also still going to be equal to that. And it'll be using star right here. So we see p1 square root of 2 is equal to f of p1 times x. So we can draw that and have that equal to p1 of x. And we can do the same thing here, where p2 square root of 2, according to star, is equal to f of p2 of x. So we have that p2 square root of 2 is equal to f p2 of x. And thus we have shown that this is equal to that. And then since these are both equal to that, and this is equal, and then the image is equal to this preimage, so it's shown that this image has two different preimages that are exactly the same thing, just written different ways. So we have now proved that not only is this closed under addition, but now that it's also closed under multiplication. So we can go ahead and check that box off as well. Then rolling right ahead, we will now be proving that f of 1 is equal to 1. Another way of saying that is that the 1 of the ring q of x is equal to the 1 of the ring q square root of 2. And one really good way to prove this is that if you see 1 in the polynomial, so in polynomials, the 1 is just a constant polynomial. And what that means is for constant polynomials, they have no x values. It's just 1 plus 0x. You can imagine 1 of qx is equal to 1 plus 0x plus 0x squared plus 0x to the n. So essentially all these x's are 0 because all their constants are 0. So only 1 is here. So if we apply the map to f of 1, we get 1, which doesn't change because there's no x turn the square root of 2. And we'll see that if we change this x, we get 0 times square root of 2 plus 0 times square root of 2 squared, and so on. So you see that all these are still going to be times 0. So we see that f of 1 is equal to 1, which shows us that the identity maps to the identity. So we've now proved that this condition holds as well. So we've now finished part 1 of the problem, proving that f is in fact a ring homomorphism from this ring to that ring. All right, so now that we've proven that f is a ring homomorphism, the second part of 2.96 was to prove that f is surjective. And what that means in other terms, if you don't know what surjective is, it just means that it's onto. And another way to look at that is that for every image in the map, there's a preimage that maps to it. So if we were to look over here, for every element in Q, a square root of 2, there is an element in X that maps to it. It's basically what it means when it says when we're trying to say f is surjective. So the first step we're going to do is we're going to let a plus b square root of 2 be an element of the ring q square root of 2. But it is important to note that we are going to impose the conditions that a and b are elements of Q themselves. And what Q is, if I haven't stated yet, is Q is all the rational numbers. So what we're saying is that we're going to let a plus b square root times square root of 2 be an element of this ring, where a and b are also going to be rational numbers, which is going to be very important. So when we have this statement right here, the next thing we can do is we will notice that when a plus bx, which we get from the original ring Q of x right over there, this can map straight over to a plus b square root of 2. The reason why a does not change is going to be very similar to why 1 maps to 1. Because a is a constant, it's a rational constant, so it's going to map straight to itself no matter what. Then b of x, bx, is going to map to b square root of 2, because again, b is a constant, it's a coefficient, so it's going to map to itself, and then x in the map goes to square root of 2. So doing that, we've shown that a plus bx now is an element of Q of x, and that for any a plus b square root of 2, as long as we have a and b are rational numbers, we can have a map from a plus bx straight to that spot in the Q square root of 2. So we've shown essentially that f of a plus bx equals a plus b square root of 2. For what this symbol means, well, I guess I don't need the for that, because that symbol literally means for any, or for all a, b elements of Q. So we've proven that f is surjective. And then so after proving the second part of the problem, where that f is surjective, we can move on to the third part of the problem, which is given that the kernel of f is equal to x squared minus 2, why then is the square root of 2 not an element of the kernel of f? Okay, so in general terms, what the kernel is, so we'll call it, for general terms, we'll call it a kernel of some function, some map phi is going to be equal to the set of r, little r, but that is an element of big R, where big R is a ring, so that's the element of a ring R, such that phi of R, so apply the map to that element of R, equals 0. So in general terms, the kernel is any element of the ring that maps to 0. So in this ring in particular, it's going to be any element in Q of x. So any element, so let's call it T. Any element T in Q of x such that f of t is equal to 0. So that is essentially what we are going to do. So we have to prove y square root of 2 does not work for that t. And that's essentially what we're going to prove in the next part. Alright, so to show that the square root of 2 is not an element of the kernel, we can do, one of the first things we can do would be to let it be an element of the kernel. And to do that, we would say let f of p, a square root of 2, equal to 0. So what this is telling us here is that if we have a square root of 2, we can have, it'll be equal to 0, which means it'll be in the kernel. But what this does is this implies to us that p square root of 2, the polynomial square root of 2, is an element of Q of x, of the polynomial values of x with real rational coefficients. And when we see real rational coefficients and you see square root of 2, that could be an alarm bell, because square root of 2 is not generally irrational. Not generally rational. Then when we extend this one bit further, this also implies that square root of 2 is an element of the rational numbers. As I just mentioned, square root of 2 can't be a rational number by definition. It's not a rational number. So that gives us a contradiction that if square root of 2 is a member of the kernel, then it must be a rational number, or it must be an element of the rational numbers, which is not. So square root of 2 is not in the initial domain, and the kernel only draws elements from the initial domain. So imagine R is RQ of X. So square root of 2 as T cannot be an element of that. So therefore, square root of 2 cannot be in the kernel.